Get started. So welcome everybody. Thanks for coming to another edition of the Visual Computing Seminar. I'm super excited that today we have visiting us all the way up from Cambridge, Massachusetts, Kartik Chandra from MIT, who is doing really interesting stuff, kind of carving out this really unique research agenda at the intersection of cognitive science and graphics, looking at human perception and how we can sort of design graphics for human perception to elicit certain kinds of experiences, which I think are, I think super fascinating. So I'm really excited to welcome Kartik, and I hope everybody else is too. So take it away.
Thank you, Daniel, for having me. It's so nice to be here in Providence at Brown, which, by the way, is a beautiful institution. It's nothing like MIT, which is, weirdly industrial. If you haven't noticed, this is an overhead projection of MIT, and maybe just to help you get your bearings. So this street over here is called Vassar Street. And on one side of the street is the STATA Center, where we have CSAIL, the Computer Science and AI Lab, where I'm in the visual computing group with my advisor, Jonathan Raytheon-Kelly, and other colleagues, notably Sue Melby, who is actually now at BVC San Diego. And on the other side of the street is this other kind of trapezoidal-looking building. And this is the Department of Brain and Cognitive Sciences at MIT, where my co-advisor, Josh Tenenbaum, runs the Computational Cognitive Sciences Lab. And as part of my day-to-day work as a grad student, I cross the street roughly 500 times a month. And I cross it in two directions. About half the time, I'm going kind of this way. I think about how we can flow insight from cognitive science to visual computing. And in particular, how can the study of the mind help us imagine magical new graphics applications and modes of expression? I am of the persuasion that the work of computer graphics is not chasing realism or kind of perfectly looking images. It's not kind of in service of the eye, it's in service of the mind. We create graphics so that we can express ideas, emotions, thoughts, feelings to other minds. And images and sounds and videos are one way in which we do it, but ultimately it's a cognitive enterprise. And the work of graphics is to create interventions in the minds of others. And so I think it's very important for us to take insight from cognitive science. And I'll give you one example of that too. The other half of what I do is cross the street in the other direction and think about how the powerful tools that we have developed over the past, decades of computer graphics and visual computing more broadly, how can those tools help us study profound, millennia-old open questions about the human mind? It's only recently in the past couple of decades that we have things like differentiable rendering. We have incredible hardware with, really unthinkable performance characteristics. How can we put these things to work to better understand the mind, to answer questions from cognitive science and cognitive neuroscience? And I'll give you an example of that today as well. So the outline for today is one example of cognitive science to graphics, one example of graphics to cognitive science, and then hopefully some time for questions. Okay. Great. So we'll start with one example of how ideas from cognitive science can influence computer graphics. And I want to start this part of the talk by, clear your mind and imagine that you are in a new city and, maybe you're there for a conference or something. And you have an extra half day or so, maybe your flight's in the evening, it's maybe 10, you've just checked out of your hotel, what do you do? Okay. You could go watch a show at a theater. Maybe you're in Sydney, Australia, and you could go see something at the Sydney Opera House. Or maybe you could just go to the airport early and you could watch people go by. Which one would you rather do? Well, most people would say, I'd rather go to the theater. It's more interesting. It's more exciting. The airport is boring. But I'll point out to you that in both of these scenarios, you will sit in a chair and watch people do stuff. It's just that in the theater, they'll be doing stuff on stage and telling a story. And at the airport, they won't be doing that. So the question is, what's the difference? Why is theater more captivating than everyday life? How do actors and animators, since it's computer graphics, how do they engage the human mind in a way that ordinary reality rarely does? I want to try to answer this question by drawing an analogy to rendering, and in particular, non-photorealistic rendering. So I'm just curious, are any of you familiar with the idea of non-photorealistic rendering? Yeah, a few of you. Non-photorealistic rendering is just rendering that doesn't strive for realism. So things like line drawing or flat art, like in the new Spider-Man movie, are examples of non-photorealistic rendering. And I think we all have an intuition that it can be really powerful. Like a drawing made with chalk on a sidewalk, a picture like this can be so expressive and so communicative, even though it's not realistic. And that's kind of surprising. Like how can being less perfect communicate more to a viewer, an audience member? Well, a lot of people have thought about this, and I want to give you one example that I really love. This is an account given by Fredo Durand, who's a graphics researcher at MIT, who in the early 2000s was thinking about non-photorealistic rendering and depiction, and he had this, I think, beautiful idea that the work of artistic depiction is not actually rendering. We shouldn't even be thinking about the work as rendering photorealistic or non-photorealistic. We should be thinking about it as inverse rendering. What does he mean by that? What is inverse rendering? Well, let's break it down. So rendering, we know what rendering is, right? Rendering means you have a scene and you do your Monte Carlo path tracing or whatever, and you sample an image that would be produced if you took a picture of that scene. That's what rendering is. And Fredo says that the work of graphics doesn't actually stop there. It keeps going. Because vision, the work of seeing and observing the world, the work that our visual system, our eyes and the back of our brain does all the time, is inverse rendering, which means we see an image, we're kind of presented with a stimulus that's kind of splatted onto our retinas, and we have to figure out, well, what scene would be rendered to produce that image? That's kind of the work of vision. It's just the opposite of rendering. And under this view, Fredo proposes that depiction, especially artistic depiction, is not rendering. It's actually inverse rendering. So the artist's job is to say, well, if my viewer, the audience member in the movie or the person standing in front of the painting, if they're doing inverse rendering to work out what is in this picture, then my job is not just to render the scene I'm thinking, it's actually to produce whatever image it takes so that my viewer perceives the scene that I'm trying to communicate. And so it's subtly and importantly different from just naively rendering. Does that all make sense? Great. Okay. So this is not a new idea. In fact, one of the references that I really love to this is from Scott McCloud's work in media theory called Understanding Comics, where he draws this picture that I think is just the perfect diagram for what I'm talking about, where someone starts with an idea in their mind and almost coincidentally passes through graphics as a medium for communicating that idea, but guess where it ends up? It ends up in another mind, and that's where the journey of graphics ends. And very recently, with some of my collaborators at CISA, we've tried to literally implement inverse graphics by optimizing over models of human vision that are modeled as inverse rendering. And I won't talk about this work today. I just wanted to leave this as a reference here if you're interested. Today, what I want to talk about is, can we apply the same ideas to animation and storytelling? The actor on the stage. How can we apply the inverse rendering concepts to dynamic scenes, not just static images? Okay, so here's the claim that I'm going to make. The claim is that if static depiction in a picture is inverse rendering, then dynamic storytelling on stage in a movie, even in a storybook, that's inverse planning. And here's what I mean by that. A foundational principle from cognitive psychology is the principle of rational action, or the principle of planning. And all it says is that people are likely to take actions that get them closer to their goals. It almost like it almost sounds silly if you think about it. But if you have a goal, you're just likelier to take actions that have a higher utility for you. So for example, if you're a person who wants to pick up a plant, you pick it up. It's just what you do. It's just rational. It's a rational action. That's what the principle is. Okay. Well, an additional principle from cognitive psychology is the principle of action understanding as inverse planning. So if you look at this person picking up a plant, you've observed an action that they've taken, you can infer what their goal was. Their goal was to pick up the plant, right? If you wanted the plant, you would pick it up. That's just rational. And so if you see someone pick up a plant, they probably wanted it. This is the idea of inverse planning, is modeling how we understand the motivations behind other people's actions. So if you observe someone plan, you can inverse plan to understand their actions. Okay. The claim we make in our paper is that theatrical acting is different from everyday acting because it's not just planning to do stuff rationally, it's actually inverse planning. It's the work of selecting the actions that would best communicate your goal to an audience who's engaged in inverse planning to understand what your goal is. So if you're an actor, it's not just that you want the plant, it's that you want your audience to think that you want the plant. And so the actions you take might be different. They might be more exaggerated. They might be, they might be louder. They might be suboptimal even. They might, it takes more energy to go like this to pick up the plant. But in doing so, it's more communicative. You really convey and express to the viewer what you want. And that's really what we're going for in animation. Does that all make sense? Great. Okay, so I just wanted to take a second first to mark that there's a difference between these two things. And to me, this is kind of the distinction between sitting at the airport watching people go by and sitting in a theater and watching characters on a movie screen. Okay, now we're going to make this concrete in a little domain that's taken from cognitive science. So this is a little grid world domain where there are these two agents that are trapped in a maze. There's a strong agent whose name is a large circle, and there's the weak agent who's the small circle, and there are possible goals that they could have. For example, either of them could want to get to the tree, and additionally, the strong agent can have some sort of social relationship with the weak agent. They could maybe want to help the weak agent get to their goal, or maybe they want to adversarially hinder the weak agent from getting to the goal. These are kind of the two kinds of relationships that these two agents could have. I should note that this domain is borrowed from the cognitive science literature. It's from Tomer Ullman's work from a few years ago. In our work, we're going to stylize this as a slightly larger domain, as a kitchen, and we're going to call these agents characters, the strong, powerful robot, and the small, weak, but still animate and enchanted block of cheese. And again, they could want either of these two goals, either the green tile or the purple tile, and the robot is strong enough to either help or hinder the block of cheese from getting to its goal. And in this little grid world domain, it's really easy to train rational policies for these agents by doing something like value iteration, or you could imagine A-star search, or any number of algorithms for planning could be used to figure out what rational agents would do in this world. Okay. So suppose I've described for you the scene, I've given you these characters, I've given you a setting. Let's say I ask you to now design for me a scene that shows that the robot is being helpful. The robot really wants to help the block of cheese get to its goal. What might you do? Well, a reasonable thing you might do is I'm going to just put these agents somewhere in the scene, and then I'm going to run their optimal policy that I trained by value iteration or something. I'm just going to run that forward and see what happens. Okay. So this is what I'm going to call naive planning. We're just going to sample actions from optimal policies for these agents. And this is kind of analogous to sitting in the airport and watching people act rationally and do their thing. If you do that, here's what happens. So watch carefully. So the block of cheese kind of moves onto the pink spot, and the robot moves onto the green spot, and then they just kind of sit there, and nothing happens. And to me, this is terrible, right? Like, this is not a good depiction of the robot being helpful to the block of cheese. And why is that? It's because the block of cheese was already at its goal. It already, it clearly wanted to get to the purple spot, and it got there. And there was just no way for the robot to help it. So no helping was evident. So this is just a poor depiction of helpfulness. We can measure this intuition quantitatively by running an inverse planner, which sees that over time, it's pretty likely that the block of cheese's goal is the pink block. And it's not clear in the beginning what the robot wants, but over time it becomes pretty clear that the robot wants the green goal because it goes there and then it stays there. But it's just like totally confused about what the robot's alignment is. Is it helping? Is it hindering? Does it not care? It's just unsure. So this is a poor depiction. Our intuition says that, but an inverse planning model of cognition also confirms that. Okay, so instead of doing that, we're going to propose to instead do inverse planning. So instead of just sampling optimal actions for these agents, we're going to optimize a sequence of actions that maximize the inverse planner's belief that the robot is helpful. So you can do this, for example, by doing beam search over the space of all possible videos, or any number of optimization algorithms. And I'll just show you what the output's like. So again, the block of cheese kind of heads towards the pink goal, but now the robot pushes it on there, and then it steps aside. And to me, this is a much more compelling demonstration of helping, because you saw someone needed to go somewhere, you push them along, you help them get there, and then you step aside. It's compelling to our intuition, but it's also it's pretty well captured by the inverse planning model. It thinks the block of cheese wants the pink goal. It's not sure if the robot has its own goal, but it's very sure that the robot has been helping from the very beginning. It knows that the robot is pushing it along to help it get to its goal. Okay, so I showed you kind of these two examples. The key takeaway I want you to have is that using inverse planning even in this really simple domain produces videos that are more expressive and more successful at communicating social relationships than naive planning. And just to confirm this, we did a little user study where we created 20 random inverse planning videos by changing the random seeds for the optimizers. 20 naive planning videos by sampling different optimal policy rollouts, and asking study participants online, is the robot in this video intentionally helping, intentionally hindering, or indifferent to the block of cheese, or is it just unclear what's going on? And what we found was that for the inverse planning videos, or our videos, on average, over 3/4 of people said that the robot was helping. Whereas if you just sample an optimal policy, typically people don't think the robot is helping. Only for a couple of lucky rollouts do people actually think that the robot is helping, even though in all of these videos the robot is performing optimal actions for a helpful robot. And this difference, I think, is exactly the difference between sitting in a theater and watching a movie versus sitting in the airport and just watching people go by. By the way, we can also do this for hindering relationships instead of helping. The same effect emerges, and we can also do this for just being indifferent. But I'm not going to show those videos for the sake of time. Okay, so I've talked a little bit about character relationships, but we know that storytelling is more than just that. A big part of storytelling is plot, and they've changed over time. Are there ways in which inverse planning can capture narrative arcs? Well, a long line of thinkers in literary theory and philosophy, in fact, even starting from Aristotle, have characterized plot as something that has a rising and then falling action. And okay, how can we make that formal? Well, Kurt Vonnegut writes that one way to make this formal is to say, one standard kind of plot is one where the fortunes of the protagonist start high, and then they get lower, and then they get higher again, right? And this is what he's plotting in this little plot. The y-axis is kind of the fortunes of the main character, and they start kind of okay, maybe they get a little better, but then they get bad, and that's the climax, and then they get better again, and that's the ending. It turns out like this kind of thing is very naturally captured in the inverse planning framework. So we can, instead of looking for a video where the robot is helping the cheese or appears to be hindering the cheese, we can look for a video where the value function of the characters, perhaps it starts low and then it rises and then it falls and then it rises. So we can even look for the cosine plot that Kurt Vonnegut drew on this board. There's kind of one additional piece that's necessary here, because in this world, there simply aren't enough degrees of freedom for interesting things to happen, because it's literally two characters. So we're going to add an additional element called Deus Ex Machina, or like the idea that sometimes storytellers just like cause something to fall out from the sky to drive the plot. In this case, we'll cause the ability to for an obstacle to fall out somewhere, anywhere in the scene, to kind of cause some plot change. And I'm gonna again play this video for you. And as you watch, first kind of look out for the narrative structure that hopefully would emerge naturally from having this kind of rise of the value function. But then also kind of reflectively think about how we didn't really bake in any of the features that you're seeing. And I'll explain more what I mean by that, but just kind of reflectively think about that. Okay, so here we go. So the block of cheese is on its way. It seems to be going towards the pink goal. It's kind of struggling. The robot helps it, but bam, an obstacle falls in the way. Okay, the block of cheese moves out of the way, the robot clears the path, and the block of cheese gets there, and now everyone's happy. Okay, maybe this isn't the most exciting story you've ever seen in your entire life. Maybe it's not an Academy Award winning short. But I want to make 2 points. Firstly, this had a story-like structure. If you just did naive policy rollouts, you would never see anything like this emerge. You would just very quickly reach some sort of equilibrium state, and nothing interesting would happen. But by doing inverse planning to modulate the value function over time, we were able to get as interesting story-like structure to emerge. And again, I think this begins to get at what's the difference between just seeing people act rationally at the airport and watching them in the theater. The second thing I want to say is the only input to this was that the value function should be modulated over time. I never told it that the robot should be helping the block of cheese. I never told it that the block of cheese should launch the pink goal. I didn't tell the block to fall at that particular moment in that particular place. All of that came from the optimizer. The only input I gave it was just that the fortunes of the characters should rise, fall, and rise. And to me, this is very interesting. Do we only have till 12:30?
No.
Okay. I thought people come at the half-hour mark and started making inferences about what might be
doing some inverse planning.
Exactly. Good. Okay, so maybe to summarize a little bit, I've talked to you a little bit about how we can model aspects of character in inverse planning. I've told you about aspects of plot we can model. In the SIGGRAPH paper that this talk is based on, I talk about a few other things. I talk about physics and mime as being an important component of acting on stage. So this is a short film by Marcel Yankovic of Sisyphus pushing a boulder up a hill, which I find really inspiring in a way. These are just marks on paper, but somehow the weight of this boulder is really palpable, and you can really feel how hard he's struggling. So in the paper, I won't talk about this in detail, but we show how you can use inverse planning to train an agent to mime that pulling a light prop, like a very light styrofoam box, can actually be really heavy. So the agent on the right is like a mime pretending that the box is much heavier than it is, and does indeed seem to struggle quite a bit. And human subject studies confirm that that's actually what's going on. People do perceive the box to be heavier. We can capture a lot more too. We can capture aspects like what's a plot twist? How do storytellers use flashbacks to surprise us and delight us? And how can we give some definition to irony, in particular dramatic irony, where the audience and the characters aren't quite on the same page about the world model? And then there's kind of ongoing work or extensions to this that we've been working on at MIT. One of them is around emotion, which is of course a huge part of storytelling. So with colleagues Tony Chen, Dave Houlihan, and Rebecca Sachs, we've been thinking about how do we take cognitive models of emotional appraisals and put them to work in inverse planning. And some preliminary data suggests that our model is actually pretty good at getting people to believe that the characters have the emotions that they actually do. I'm also really interested in this idea that you don't actually need video to tell a story. You can tell a story even with a single image. And this is work we presented at NeurIPS with Tony Chen, and that's what I'm going to talk about next. But first, I just need a break to take a drink of water. Okay, 1 sec. So that was the first part of my talk where I gave an example of how cognitive science can help us imagine new modes of expression in computer graphics. Now I'm going to give you one, I think, really striking, surprising example of how algorithms and tools from visual computing can help us make progress in cognitive science. So this is, the problem setup is going to be a cognitive science problem, but the tools are going to come from graphics. Okay, so here's the setup. Ernest Hemingway famously wrote the shortest short story ever, and it's 6 words. It goes, "For sale, baby shoes never worn." And when I read the story, I'm like, was that even a story? Oh. Yeah. It kind of hits you at some point, like what happened, and the kind of the rhetorical power of just this little snapshot. No actions have occurred here. This is a description of a state. There's nothing dynamic at all, and yet we can infer a story. More generally, humans have this astonishing ability to make dynamic inferences about each other, even from static snapshots. I'll give you some examples. Okay, so here's this kid. This kid is stacking the cups. Even though this is a static image, you can kind of guess like what's going to happen next. He's going to put that in. Okay, what's happening? Who is moving in which direction? You can kind of make all of these inferences, even though nothing is moving. This is a static image. How is this kid feeling? What just happened? What was going through his mind? How did he get into this situation? What's going to happen next? You can answer all of these questions, but again, static image, no motion. You don't get the derivative, you just get the point value. Okay, crime scene investigation. You don't get to see anything dynamic about the crime. All you get to see is the trace that's left behind. It's a static trace, but you can still, especially a skilled forensics professional can definitely work out how did this happen? Like the time series, the sequence of actions that led to this state being left. And of course, as I alluded to earlier, in art, a painting, a sculpture, a moment, a comic book panel, all of these things, none of these things move, but they all, well, they move us, perhaps. They tell stories. One question that I think has animated a lot of cognitive scientists is, how do we do it? How do we make inferences like this pretty much immediately, very robustly, with very little pre-training data? That's temperature warning. Should I be concerned about that?
No,
just great. We make these inferences. It's kind of almost on autopilot. It's very intuitive. How do we do it? Like, what is the computation that's occurring? I told you a little bit earlier in this talk about this idea of inverse planning as an explanation for some action understanding. But note that in inverse planning, you have to see actions, right? We conditioned our models and observed action. Here, we only get a state. We don't get to see any actions. We only get to see an image, a static snapshot. So how can we still make these models work? So I'm going to now move away from this abstract framing with lots of pictures and give you like a computational framing of this problem that we can then apply algorithms to solve. Okay. So here's the problem setup. Suppose there's a world with possible goals in it, like these 3 checkered flags, and you spot an agent in some state X. So you spot them right there. And additionally, maybe you know that they could have come from somewhere, you have some prior belief about where they started. And the question is, now, where do you think they're going? So for example, here, you might say they're pretty likely to be going towards goal G or maybe the middle goal. It's kind of unlikely that they're going towards the bottom goal because like why would, no matter where you started and no matter what you did, it's kind of weird to be observed kind of closer to the top half of this world if you were going towards the bottom goal. That's the kind of inference we'd like to capture. One way you could do this is by sampling a whole bunch of paths from possible start states to possible goals, and then conditioning on being observed here. And this is a thing that cognitive scientists have tried in the past. There's this beautiful, I think, paper by Lopez-Brau and Kara Inter and colleagues that attempts to do this, and they get like really nice correlations with human judgments. So the system seems to work, but it is extremely sample inefficient. And the reason for that is if you are just sampling paths from starting states to goals, well, most of the paths just don't pass through the point you've observed. So you end up throwing away nearly all of the work you do, and you only keep those lucky paths that actually fit your observation. Okay. So I was reading this paper and I was talking with Tony, and we thought, there's kind of an easy fix to this, right? There's nothing deep about what I'm about to say. What I'm about to say is this: trace paths in both directions. Start here, trace a path forward to a possible goal, and then trace a path backwards to a place where you would have started. And now you're guaranteed that your path will pass through this spot you observed, so you don't have to throw anything out. So orders of magnitude more sample efficient. Orders of magnitude more sample efficient. Again, this is, there's nothing clever about this. We were just sitting in the office thinking about this. But the piece that I'm proud of, I'm going to say next, which is the following. Does this remind you of anything? Is there anything like familiar about what's going on here? And if not, that's okay. It took me like a while to realize what was really going on here. I'll give you a pictorial hint, however. Here's the pictorial hint. Does this sound familiar? Like, is there something kind of reminiscent of something from graphics? It turns out that we can draw a one-to-one analogy between the paths that light rays take in a scene and the paths that people take in the world, where every reflection or kind of surface interaction that light has, and every stochastic bounce it has because of the BRDF is exactly analogous to someone reaching a choice point and then making a rational decision based on their planning system. Okay, this seems like maybe kind of a cool insight, maybe useful. It turns out it's extremely useful because now the past 30 years of research into Monte Carlo renting algorithms is immediately applicable to this problem in social cognition. So bidirectional path tracing, irradiance caching, all of the Russian roulette termination, all of these techniques that you can read about in like Matt Farr's textbook, these are just immediately applicable. We can immediately put them to work and make this algorithm even more efficient. So, okay, how does this round up? Well, we can capture the kinds of intuitions people have about social scenes remarkably well with only like 10-ish samples. And I'll give you a little example of this. This is going to be like very cognitive science-y. Here's the example. So suppose you see someone in this like little grid world. They started somewhere here and then they're on the move and they're trying to get one of the 3 gems: red gem, green gem, or blue gem. Well, which one do you think they're trying to get? Most people would say they're probably going for the blue one, right? I mean, it's the one they're closer to. It would be weird to end up there if you're going for the red gem or the green gem. Okay, our model captures this inference. So actually, we can do this for every single observed square. So if you see the person right here, yeah, probably they're going to the blue gem. If you see them here, probably they're going to the green gem. Note that, for example, if you see them here, it's not clear. They might be going for the red gem, or they might have started here and they might be on the way to the green gem. So there's some ambiguity. Our model captures pretty much exactly what humans say. So if you go and ask people on the street, or in our case, ask people on Prolific, what do you pink, like what's your subjective belief, they capture exactly, or almost exactly, like with high R squared, like what our method says. But for comparison, if you do the rejection sampling I showed on the previous slide, you get this extremely noisy sample that doesn't nearly resemble what people do, and often like even fails to find any answer at work at all. So if you don't want to think about the cognitive science here, just think of this as like a rendering problem, and notice that like the S-sim between the first two is a lot higher than the S-sim between the second two, where this is ground truth, this is humans. Okay. Okay, I'm now going to just show you like 6 more examples of how well this works. But I'll go through them kind of fast because I don't think you're actually that interested. I just want to make the point that this one idea works in a wide variety of different circumstances. Okay, so here we go. Here's one. So we can make this like grid world more complicated. Suppose the gems are behind doors that are locked, and to open a lock, you need a key of the same color. So, okay, if you spot someone over there by the green key, they probably want to get the green key to open the green lock to get to the blue gem, and our method captures that inference. If you're spotted there, high chances you're going to the blue gem. People say the same thing, but if you do rejection sampling, you get a pretty noisy estimate, often fails to converge. Okay, you might think, okay, maybe this only works in these like spatial planning tasks for some reason, but here's something that's like not spatial at all. So here you have these like little blocks with letters on them, and someone's like trying to stack them together to build a word. If you see them in the middle of this task and you see this as the arrangement, you might wonder which word are they trying to spell. Most people say they're trying to spell the word rigged, R-I-G-G-E-D. That just makes sense based on kind of my intuitions about what's going on with the the model captures that, but here's the more interesting thing the model captures. Which blocks are likely to have the agent's fingerprints? So I'll actually just ask you, do you think it's likelier that this block has the person's fingerprints, so they touched this block recently, or this block? So raise your hand if you think of this one. Raise your hand if you think of this one. Okay, so there was like a slight preference for the G. Yeah, so our method captures what a sample of humans says like pretty well across all of these different blocks. So if you ask between E and G, it kind of reproduces the same difference. Whereas prior work, even if you take like thousands of samples, you don't get any inference. And you can do this with other arrangements of blocks too. Okay, we can also do this in domains where the agents have partial observability. So here, like a student leaves their home and they're trying to decide which food truck to eat food at. This is like a classic cognitive science stimulus, but there's this big wall, so they don't know what's around the corner. And you see them look around the wall, and then the question is, do you think they like this food truck or not? And the intuition people typically have is like, no, they don't, because they're going around the wall to see if there's something better available. And the model captures that even from the snapshot, and it does it like pretty richly. It gets a lot of the like subtle detail that people have. And finally, we can also do this in kind of intuitive physics scenarios. So if you see the kind of classic cart pole demonstration from reinforcement learning, suppose you see the cart kind of in this position, you probably think the pole is falling down and the cart is like chasing to catch up. Whereas if you see it kind of nearly upright, you might think, oh, I'm not really sure whether the cart is going this way or this way, but it's probably not moving too fast. It looks pretty balanced. And the model also recovers pretty reasonable judgments for that. Okay, finally, it works in cases with multiple agents. So if you have 2 agents in this room and maybe someone is chasing someone else and there are possible exits, people have the intuition that probably like this guy is chasing this guy who's trying to go out of this door, and the model recovers this inference. Okay, so I just gave you like 6 examples of how this one idea can apply to a wide variety of problems in cognitive science, but at the base of it, it's all it's all a computer graphics trick. It's algorithmic tools that were developed to do rendering. And just to end this presentation, I wanted to talk a little bit about how can we bring this back to graphics? How can we take this tool, that we've applied to cognitive science, how can we now take this cognitive insight and then bring it back to graphics? This is ongoing work. This is stuff that I've been thinking about over the past couple of months. Is artists frequently represent dynamic action in static images and sculptures by what I like to call like inverse snapshot inference. So think about a sculpture like this, where it tells a story. There's even a little bit of motion. I think you can kind of tell how the cloth might be draping. There's definitely emotion, but all of this you're getting from something that doesn't move. And think about a sculpture like this, which is abstract. There are no agents whatsoever, but notice that if you look at this naively, you might expect it to immediately fall over. And so there's something kind of surprising and pleasing in the surprise that it doesn't do that. That's another example of kind of dynamics and statics coming to attention. Or think about a painting like this one. This is by Correggio with the Abduction of Ganymede. I really love this painting. But again, notice like, think about, I mean, not just the motion here. Look at the cloth there. Look also at the dog, like, you can kind of guess which way the dog is going just from the static snapshot. And I think it'd be really wonderful to be able to give artists tools to depict dynamic motion, stories, emotion with just static snapshots. So this is stuff that we've been working on. But I wanted to zoom out even more and kind of give you, for me, what the bigger picture is. And the bigger picture for me is engineering human expression in all its forms by inverse cognitive modeling. So, I've given you some examples of depiction, and there's more depiction in work that I haven't covered that I can talk to you about or point you to. But, if we were to play for higher stakes here, we don't just depict, art, emotion, storytelling. We express all the time in everything that we do. So, for example, I've been thinking a lot about like pedagogy, right? Like pedagogy is the expression of ideas. Can we model it in this kind of inverse cognitive modeling framework? Can we design pedagogical tools by putting ideas from cognitive science to work and combining them with powerful tools from computer graphics? I'm going to leave that blank unfilled for now, and if you're curious what I think goes there, you should ask me over lunch. Another example of this is explanation, which is distinct from pedagogy because you can explain not just to teach, but maybe to just get someone unstuck in the moment. How can we model explanation? How can we build tools that can explain themselves and help help their users get unstuck when they're confused about what's going on? And again, I just want to bring back this picture from ultimately, I want to use these ideas to build tools that help people take the things that are in their minds and somehow transmit it to other people's minds and vice versa. So that to me is the bigger picture of where I am and where I'm going. Thank you for having me. It's been really lovely, and I look forward to talking with more of you. And yeah, that's all I thought. Thank you.
We have time for questions. We have them. Yeah.
Hey, Kartik, amazing talk. Really enjoyed it. One of the things which I started thinking way back at the start of the talk is just about how the inverse planning can go on recursively for like a lot larger loops, where the sort of in a lot of art movies, you see that they expect the audience to know something, and hence they even plan what the audience would expect, and then perhaps have some ideas. So, do you have any things you're working on where the inverse planning loops more than twice, like kinds of loops?
Yeah, that's a great question. So I gave this talk at SIGGRAPH, and then since the SIGGRAPH was in LA, and my family's we currently live near San Francisco, and so I went back and I met up with some friends from Stanford right in my undergrad, and so those of you who have been to Stanford might know it's near this downtown area, University Avenue, where there's this huge theater called the Stanford Theater that shows these old time black and white movies. And so on a lark, some friends and I went to go see this movie called Charade. Has anyone seen this? I think it's from the 70s. The title theme is composed by Henry Mancini, who also composed the Pink Panther theme. has Cary Grant and Audrey Hepburn. I don't know, it's a cute movie, but this movie has characters that are constantly deceiving each other, and so there's like a plot twist approximately every like 12 minutes in this movie. And so as the audience, you're watching, you're like, aha, I figured out what's going on. And then 12 minutes later, no, oh, now I know what's going on. And then you watch and it's like, no, that's not quite it either. Now I'm confused again. And it kind of takes you on this journey of surprise. And that got me really interested in this question of surprise. It's something I've been thinking about. I've had some nice conversation with cognitive scientists at Stanford, like Toby Gerstenberg, if some of you know, about this. I've also been reading about what literary theorists think about surprise. So Vera Tobin has a book called Elements of Surprise, and I think a lot of kind of surprise and deception and storytelling, both characters deceiving each other, but also the author deceiving and then kind of pulling the wool from the eyes of the reader or the audience member, all of that can be described as maybe higher order inverse planning. So I do think there's a lot of interesting stuff to do here, and I'm kind of curious how this can be made to work. But yeah, no, thanks for the question.
Other questions? Go for it.
So another thing which struck me was it's really nice to see that the model is able to sort of make these inferences in sort of this limited set of possibilities. When we sort of like start thinking about inverse planning with like actual humans with like a large scale possibilities that they might consider, I thought the biggest trick comes at actually modeling the human sort of the inverse planning part on which you're applying inverse again. And my question is like, how do you solve that? Do you think about solving it? Is there something for the inverse planning part on top of which you're applying?
Yeah, that's also a really good question. I showed you a bunch of these small grid worlds or like the little character on the hill. But you might ask, no one would ever watch a movie that took place in a grid world, right? I think one answer to this comes from recent advances in machine learning and data-driven AI, and in particular, the way language models have been able to capture a lot of like ambient knowledge about the world and the kind of rich space of possibilities of things that could happen. My colleagues at MIT, in particular, folks like Lionel Wang and Alex Lev and Lance Ying, have been exploring very deeply how can you take these principled Bayesian models of human cognition, for example, things like inverse planning, and combine them with the things language models are really good at, which is coming up with possibilities, even if they're not correct, but at least kind of brainstorming them. And they recently have this paper on the neural symbolic inverse planning engine that begins to get at some of this. And I think that's one like possible scaling route here, and one that I think is super exciting, and I'm curious what could be made with that.
Thanks.
There are no further questions for now. Let's thank our speaker one more time. Has some time to schedule.